Hello, my name is Connor Houghton. I'm here to present my honors thesis poster, and the title of the project is Universality Parameterization Extension of Electron-Positron Angular Spectra in Extensive Air Showers. So, a quick rundown of what we're looking at here is that a cosmic ray, which is a high energy particle from deep in space, like a proton or something, is emitted by a star or a supernova or something, and it comes and hits the atmosphere. When it hits the atmosphere, it creates a cascade of smaller particles, like a bullet would explode when you shoot it into water. If you look at all of the different angles, momentum angles that the particles within the shower make with the horizon, and then you look at their energies, you can create a two-dimensional histogram with the number of particles as the elevation, and on each axis you have the momentum angle and the particle energy. A paper written by Lefebvre et al. Gives the shape of this histogram in an equation, and in the study we wanted to extend the range of data that you could plug into this equation and get back accurate results. So essentially, why you would want to do that is if you had some limited data about a particle shower, you can work backwards with the equation to tell you other things about the particle shower. So we generated our own particle showers using Corsica simulation software at 10 different primary particle cosmic ray energies, and we looked at a few different things. Number one, we looked at stage dependence. The stage is just a parameter that tells you the time before and after the shower max, which is the point in the shower when there are the most particles. We didn't find any dependence of this distribution on shower stage. And then, once we determined that it was stage independent, we looked at the primary particle energy. We wanted to see if the energy of the cosmic ray that came into the atmosphere changed anything about the distribution or the angular spectrum. So we took the parameters in the equation that tells you the angular spectrum, and we looked at certain aspects of those with respect to the primary particle energy. And we ended up doing a lot of equation fitting or line fitting so that we could work backwards and plug all of these equations into each other and recreate the data based on only the secondary particle energy, that is, using the particle energy in the shower, and the primary particle energy that came into the atmosphere. These reconstructions seemed to work pretty well, and we ended up being able to pretty closely create the original angular spectrum using just those equations. You can see here on the screen these colored lines and these black lines. The colored lines represent the parameterization, or rather the equation reconstruction, and the black lines represent the actual data observed in the software. So you can see that they're pretty close, and that's what we sought to do, is recreate the data using parameterizations and these new equations that we came up with, so that we now have another degree of freedom within the angular spectrum. So if you have some of this information, you might be able to work backwards and determine the primary particle energy. In conclusion, what we did was we looked at the angular spectrum with respect to two different degrees of freedom: secondary particle energy and primary particle energy. We created new models to give you the angular spectrum with respect to primary particle energy.